Assalamualaikum. For the introduction, rotational system and crucial in mechanical engineering, they are the basis for things like turbine, engine, and gyroscope. This system control how torque, inertia, and angular acceleration work together for smooth operation. Knowing how torque and angular acceleration connect is key to making machines work better and save energy. This knowledge helps engineers design machines that can handle different loads and conditions. Advancing technology and industry, studying this system also explains energy exchange and mechanical stability, showing the importance of rotational motion in engineering today. For the objective, theoretical derivation is crucial for establishing the relationship between torque and angular acceleration, providing a fundamental understanding of how these forces interact. Experimental validation is essential to measure and confirm this relationship through rigorous experiments, ensuring that the theoretical concept hold true in practical applications. Additionally, rotational inertia analysis examines the impact of rotational inertia on the system, revealing how inertia affects the stability and performance of mechanical components. By combining these three aspects, derivation, validation, and analysis, we gain a comprehensive understanding of rotational systems, which is vital for the advancement and optimization of mechanical engineering technologies.
The structural methodology for understanding the interplay between torsional, angular acceleration, and rotational inertia. This study integrates the theoretical derivation, experimental validation, and analytical insight to provide a comprehensive understanding of rotational dynamics. This understanding is critical for optimizing the performance and stability of mechanical systems, with implications for energy efficiency and industrial advancement. Our methodology is structured into sequence iteration as number 1, theoretical derivation, number 2, experimental validation, and number 3, analysis of rotational inertia. Each phase is designed to build upon the previous, combining theoretical frameworks with a practical experiment to verify and analyze rotational motion principles. In the first phase, we derive the theoretical relationship between torsion and angular acceleration using Newton's second law for rotational system. Torsion equals moment inertia multiplied alpha. We extend this principle to various rotational systems such as solid disks, hollow cylinders, and point masses, developing mathematical expression for each configuration. The second phase validates the theoretical relationship experimentally. A rotational system such as flywheel or rotational platform equipped with sensor is constructed or utilized. Instruments like torsion sensor, accelerometers, and high-precision encoded capture apply torsion and resulting angular acceleration. Non-torsion are experimentally applied and angular acceleration are recorded under controlled conditions, minimizing friction and environmental inconsistencies. In the third phase, we analyze the effects of rotational inertia. The moment of inertia is varied by adjusting the mass distribution of the rotational system, adding or removing weights, or recovering mass placement. The experiment is repeated for each configuration, observing changes in angular acceleration under identical torsion conditions. This phase highlights how inertia governs rotational motion. Data from the experiment is processed and analyzed. Torsion versus angular acceleration graphs are plotted, verifying the linearity of their relationship. The slope of the graph corresponds to the moment of inertia, confirming the theoretical prediction. Experimental errors such as friction, air resistance, or sensor inaccuracies are evaluated to ensure reliability. Deviations from the theory are analyzed to refine our understanding. The study concluded that relationship between torsion and angular acceleration is linear, with the slope representing rotational inertia. Changes in mass distribution significantly influence rotational motion, reaffirming the role of inertia. Application Application enhancing energy efficiency in rotating machinery and improving stability in industrial processes. These findings have a far-reaching in application for modern engineering and industrial optimization.
Thank you very much to my friend. My name is Mohd Ahmad, and I'm going to continue with the calculation, analysis, and also the free body diagram. So from the data given on the question, we managed to illustrate the free body diagram for this question. And next we continue with the calculation. So from the calculation, we managed to get the normal forces from for A is 5,762.52 Newton for the front wheel, and the normal forces that act on B, which is 8,918.18 Newton for the rear wheel. So from here, we continue to make a two graph, which is the coefficient of kinetic versus acceleration, and also one more is for the normal forces which act on A and B versus the acceleration. So for the acceleration, we managed to get 1.19 meter per second square. So for the analysis, so for the front wheel, which is the 5,762.52 Newton, and the rear wheel, which is 8,918.18 Newton, so the distribution indicates that the rear wheels bear a larger load compared to the front wheels. So for the weight distribution, the greater load on the rear wheels suggests a rear heavy design, which is typical for the vehicles where the driving force is applied at the rear wheels. As an example, rear wheel drive cars. So this distribution is important for traction and stability, especially during acceleration. So for the dynamic stability, the car acceleration of 1.19 meter per second square is efficiently achieved due to the larger normal force on the rear wheels, which provides better traction. The stable normal forces acting on normal forces A and B during acceleration indicate predictable and reliable vehicle dynamics. A rear heavy load distribution improves traction, essential for effective acceleration and maintaining control. So for the practical implication, so for traction, it is a greater load on the rear wheels enhances the traction, which is crucial for a rear wheel drive vehicles. For the stability perspective, the stable normal forces ensure consistent and predictable handling, important for safety and performance. For the friction utilization, efficient frictional force utilization allows the car to achieve optimal accelerations. Okay, next is for the evaluation. So constant normal forces, which is the normal force on A and B, remain constant, indicating a stable weight distribution on the front and the rear wheel of the car. So the front wheel bear more load, which is 8,918.18 Newton compared to the rear wheels, which suggests that the car is designed to have a heavier front wheel. This is important for the stability and steering. So for the friction and acceleration, the frictional force calculated using coefficient of kinetic, which is 0.2, and the result of normal force on B, which is give us the acceleration of 1.19 meter per second square. This shows that the car accelerates efficiently given the coefficient of friction and the forces acting on it. Next is the dynamic stability. The constancy of the normal forces and the resulting acceleration suggests that the car dynamics are stable and predictable under the given conditions. The car motion is primarily influenced by the friction between the rear wheels and the road, as indicated by the calculations. Lastly, practical implication. The analysis highlights the most important of maintaining proper friction and weight distribution for optimal acceleration and stability. It also underscores the role of kinetic friction in determining the car's performance. Thank you very much.
Assalamualaikum. I will continue this presentation. My name is Adlin. For this project, I will talk about discussion for this project. For the rolling acceleration is depends on geometry of the cylinder, angle of inclination. For moment of inertia, we have lower moment of inertia is faster rolling for solid cylinder. For higher moment of inertia, we get slower rolling, which is hollow cylinder. By friction was sufficient to prevent sliding, injuring rolling motion. Um, for this project, we get essential for maintaining rolling motion, prevent sliding, aligning with theoretical assumptions. For mass distribution, solid versus hollow cylinder illustrate the impact of moment of inertia. We get higher inertia is greater resistance to rotational acceleration. For this project, the result align closely with theory, validating principle of rotational dynamics. We get the interplay between friction, mass distribution, and acceleration. For the future direction in this project, we use advanced tool, which is automate timing system. This is the investigate more material and shapes and explore effects of varying friction coefficient. Next, this project is strong agreement between theory and experiment. We are framing rotational dynamics principle for future experiment could improve precision and explore varying materials and friction coefficient. So that's all. Thank you. I will pass.
So here guys, I will continue this presentation in part of conclusion. In conclusion, the case study of the prototype car illustrates the critical interplay between weight distribution, friction, and vehicle dynamics. The analysis revealed that with a mass of 1.5 mg, which is 1500 kg, and a center of mass position is 1.3 meter from axis and 0.9 meter from the rear axis. The car acceleration is a significant induced by the force acting on it. The rear wheels, which are responsible for driving the vehicle, experience tipping due to a coefficient of kinetic friction, which is UK of 0.2, leading to calculate frictional force of 1204.16 Newton. This force serves as the net force propelling the car forward. Applying Newton's second law, the resulting acceleration is approximately 0.8028 meter per square. Okay, so next, take this case study implies that the slipping of the rail wheel and the limitation imposed by friction critically affect the car motion, restricting its acceleration capabilities. Understanding this dynamic is essential for optimizing vehicle performance and stability, particularly in scenarios where rail wheel slipping may occur. Overall, this analysis not only reinforces foundationally principles of rotation dynamics, but also highlight their practical implication in automotive engineering and design. Okay, so here guys, that's all for our group, and thank you for give attention, and thank you.